We now use the Lorentz transformation to transform velocity between frames. Recall that a velocity is equal to the rate of change of a position. So we need to find these space and time intervals in order to calculate velocity. So recall that the Lorentz transformation for x is as follows, and the Lorentz transformation for time is as follows. So if we take an interval, so delta x prime, between say two positions 1 and 2, we'd have an x2 prime minus x1 prime, and then transforming, we have gamma x2 minus ut2 minus gamma x1 minus ut1, and then we proceed algebraically to find gamma x2 minus x1, and then gamma into gamma u into t2 minus t1. So this is delta x and that's delta t. So we have a gamma delta x minus gamma u delta t, and finally we have gamma delta x minus u delta t, which has a similar form to the Lorentz transformation. We can do something very similar for time, and we find that delta t prime is equal to gamma delta t minus u delta x over c squared. And for y and z, things are very simple. Delta y prime equals delta y, and delta z prime equals delta z. We are going to find the ratio of intervals as the time interval tends to 0. So there's a limiting process. So we can work with these infinitesimals. So we say dx prime is equal to gamma dx minus u dt. We know that dy prime equals dy, dz prime equals dz, and dt prime equals gamma dt minus u dx over c squared. So these are infinitesimals where we have let delta t tend to 0 in the limit to get dt. And so all of these are in the limit of delta t tends to 0. Now to find the velocity in s, we have a certain velocity v, which is equal to vx, vy, vz. These are the three components. And each of those is given by the ratio of these infinitesimals, and we can use that process. There is a more rigorous limiting process we can use, but this is sufficient for our purposes. So we find that in s prime we have a velocity given by vx prime, vz prime, vy prime, vz prime, which in turn is equal to dx prime dt prime. Note that we divide by dt prime, dy prime dt prime, and dz prime dt prime. So now we're going to use these infinitesimals to find out what these velocity components are in s prime. So let's start with vx prime. So vx prime is equal to dx prime divided by dt prime. And we have dx prime up here and dt prime there, so we use gamma dx minus u dt for dx prime. And we divide by this dt prime, so which is gamma dt minus u dx divided by c squared. So we can divide through by gamma top and bottom, and then we're going to divide by dt top and bottom as well. And what does that give us? Well, it gives us a dx dt. Du dt divided by t is just u, and below the line dt by dt is just 1, and we have a u then dx by dt, and that is divided by c squared. So the result of that is that we have vx prime is equal to vx minus u divided by 1 minus u vx divided by c squared. And that is the Lorentz transformation for the x components of velocity. In the y direction, we are going to follow a very similar procedure. We divide the dy prime by dt prime, and then we write that out as dy, which is the same, but dy prime equals dy, and the dt prime is given by this, and then we divide top and bottom by dt. That's the important step. And so dy dt is vy, and below we get gamma. Now dt divided by dt is 1, u is a constant, dx dt is there and divided by c squared. So finally we have Vy divided by gamma into 1 minus u, so dx dt is just Vx, u Vx upon c squared. So notice that the Vy transformation has a gamma below the line, but this factor here, 1 minus u Vx upon c squared, affects both. In the z direction, the Vz prime follows an identical path to Vy prime because they're both lateral and they both have the same form, namely that dz prime is equal to dz. We replace dy prime by dz prime and dy by dz, and otherwise everything stays the same, so we can immediately write down the transformation which has the same form as that in the y direction. For the inverse transform, what we're going to do is replace u with minus u. So we'll take wherever there's a u, we'll convert it to minus u because that is the essence of the transform, and all primed quantities will be interchanged with unprimed quantities. So if we start with Vx prime is equal to Vx minus u divided by 1 minus u Vx upon c squared, if we transform that, we change the Vx prime to a Vx. We change the Vx prime here, Vx to a Vx prime. The minus u we change to a plus u, and down below the line we change the u, the minus u to a plus u, and the Vx to a Vx prime. So there we have the inverse transform in the x direction. We follow a similar pattern for the Vy prime transformation, where we have a 1 minus u Vx over c squared, and then when we find the inverse, we're going to exchange Vy prime for Vy above and below on either side, and then here we have gamma 1, instead of minus u we have plus u, and we have a Vx prime divided by c squared. The Vz prime has the same law, so we follow the identical procedure for the y velocity coordinate. So we get Vz equals Vz prime divided by gamma into 1 plus u Vx prime over c squared. Notice, by the way, that these transformations become the Galilean transformations in the limit that v and u are very close to 0, or they are small compared to the speed of light. In that case, since u is small compared to c and Vx is small compared to c, this term becomes close to 0, becomes negligible, so we can subtract that term away and we just get the Galilean transformation. With the gamma is close to 1, so that becomes 1 below the line, and Vy prime equals Vy, Vz prime equals Vz, and Vx prime equals Vx minus u is the Galilean transformation for speeds very much less than the speed of light.